Thank you very much, Ewan, and thank you very much for entertaining me here. Can I first apologize that my French is terrible, and you would not want to hear me for 28 minutes or any longer speaking French, so you'll have to suffer in English. Can I start by asking who thinks there is life in the universe outside our solar system? Anyone think there is life out there? Okay. Anyone think there isn't life out there? So I have many people think there are, a few people think there aren't, and a few people can't understand my English. I'm not going to answer that question. I don't know the answer to that question, but what I think is we're living in a time when we have the tools where we'll be able to answer the question. We'll be able to directly probe whether there is life living in planets going around other stars. And I think that's a very exciting situation to be in, and one which has troubled mankind really for a long time. So I don't expect you to read this quote from Democritus, but basically this is 2.5 millennia ago, and he's worrying about whether there is life in planets going around other stars. So this is an age-old question, and I think we're very near to answering it. What I'm going to tell you is how I think we will find the answer to the question. So to start with the stars themselves, of course, there are a lot of them out there. Our galaxy has something like 100 billion stars in, 10 to the 11 or 10 to the 12 stars in. Huge number. There are a similar number of galaxies in the universe, about 10 to the 11 galaxies in the universe. So if you multiply those two numbers together, you realize that in the universe as a whole, there are 10 followed by 23 stars. Absolutely unthinkable number. Though interestingly, it's approximately Avogadro's number, which is the number of molecules in a liter of air floating around in this room. So there's a certain sort of symmetry there. But it's a very, very large number of stars out there. And so, of course, what we want to know is anybody else out there amongst them. And you can think that there are three possible ways of answering this question. You can hope or you can worry. If Hollywood gets hold of it, you get very concerned if any aliens visit us, because they always seem to want to wipe us out. You can listen for their signals, or you can look for them. And I'm going to hope to persuade you that looking for them is the answer, and the other two are rather fanciful. If you go on the internet, it's very easy to find pictures like this, and I will note the internet page I got it from. There's lots of noise about this. There's no scientific evidence whatsoever for any visitation from alien beings, from other planets, other civilizations or anything. Though it's great fun to talk about and it's great fun to make movies about, it is not reality as we know it. So I'm not going to spend any time on this at all. It's not something that you can put scientific investigation into. More seriously, and it's actually where I took the title of my talk from, is the search for extraterrestrial intelligence, normally called SETI. And there have been a number of these experiments, and they're serious scientific experiments. I'm going to talk about one of them because it was the biggest and most systematic, but it's not the only one. And I'm also going to try and persuade you why I think this is a waste of money. To be honest, it's never been done with taxpayers' money. It's always virtually been done on private finance, but I think it's a very low chance of succeeding. So SETI, the SETI project ran out of Arecibo, out of this natural telescope in the ground in Puerto Rico, for about 10 years until about 5 years ago. And what they did was to survey all the stars in the local galaxy to detect whether they were sending a signal to Earth which could be interpreted as a sign of intelligent life. People actively signaling, saying, we are here, listen to us. And they got, the most innovative thing in this actually was that they got a huge amount of data, and they got everyone to download the data and do it as a screensaver. Now, this has now become quite common, but this was actually the first experiment to do this. And they used to keep statistics on their website of how many downloads they had. They stopped when it got beyond 500 million. So all I can tell you is that they had more than 500 million downloads analyzing the data. If I have a slightly older audience, I always ask them if anyone did this, but I suspect there's no one here. Did anyone do this? Yes, you did. Did you find anything? Nope. Nope, because what did they find? Nothing. Right, they looked everywhere, but they found no signal. Now, I have to say, at least that's honest, because I'm sure it's the right result. And it's very tempting to always say you find something. So that's been a serious scientific attempt to do this. Let's start at the other end. What really has happened in your lifetime is there's been a major change in science, in astronomy, because we've discovered planets. We now know, 20 years ago, we only knew about the solar system. We now know that planets are really very, very common. And this is a nice picture. It's an untypical picture, but this is a star with a planet. And if you can read that, it says it's 55 AU is the distance. The AU is the astronomical unit. It's the distance the Earth orbits around the sun. So this is 55 Earth orbits away. It's a huge distance. This will be a very, very cold and not very nice planet to live on. Well, you won't live on it. It's too cold. But it's untypical, but you can, because of that, you can take a picture. That's not how we know most of the planets are there. We use different techniques. The original technique was something called radial velocity measurements, where you have a star here. There's a star. Well, actually, let's have my head as a star. And you have a planet. No, we'll do it with this. And you have a planet going around it. And you think of the planet orbiting the star, but it's not quite like that because the center of mass has to stay constant. So the star itself wobbles very slightly as it goes round. And the result is that if you look at the light from the star, as the planet orbits around it, you can see a little wobble in the light from the star. And you get pictures like this. This was one of the very early detections, a planet going around the star 51 Pegasus by Massey and Butler. And you get this characteristic sine curve showing that there's a planet there causing the star to wobble just a little bit. So it's an indirect detection. And what you get from this, you get the year. This particular year was a bit more than 4 days. This method is very good at seeing very large planets very near the star. And these planets whiz around very quickly, so they have short years. So with this technique, if you were looking at our own solar system, the current sensitivity is you can see a wobble of about 0.5 meter per second in the star. Jupiter causes the sun to wobble by about 15 meters per second. So if you're sitting somewhere else in the Milky Way looking at the solar system, you would know there was Jupiter. You would also know there was Saturn, but Earth only causes a wobble of about 9 centimeters per second. We would still be invisible with our technology. So you have to realize in a lot of these things there's what's called observational bias. We see what is easy to see. We don't necessarily see what is there. Anyone know what this is? Nope. Venus, transit of Venus. Anyone see this? Been 2 transits of Venus in your lifetime? Yes, you have a nod there. Yep. So it happened, 2004 was spectacularly good in England. You can see it very, very clearly. 2012, it wasn't so good because it was really going to happen very early in the morning, and certainly in London, the weather was terrible. I got out of bed at 5 in the morning, looked out of the window, and went back to bed again. The problem is, if you didn't see it, most of you didn't put their hands up, I'm afraid you've missed it, because the next one isn't until 2117. So this happens on a very strange 190-year cycle where it happens 2 times rather close together and then doesn't happen for a long time. Now, if you were doing an observation, and I wasn't doing this observation, but people were, and said, right, we have the sun and it's shining, and here is all the light from the sun, and then Venus comes in front, and I reckon that's about 0.5% of the area of the sun. What you'll see is that the sunlight will dip just a little bit by 0.5%. And you'll be able to watch the transit because the sun is not quite as bright, and then it'll transit and the sun gets brighter. And it happens that by accident of geometry, there are a number of planets that when you look at them from Earth, they orbit so that when you look at them, they pass in front of their star, and they block the light from the star, and then they go behind the star. And you can see this, you can see the transit. It's purely a question that we happen to be looking at those planets at the right direction. And there are people realize the importance of these planets, and I'll come to that in a minute. So there's been a number of dedicated space missions looking explicitly for these planets. The first one was actually a French mission called Corot, which was launched in 2006. They're normally 3-year missions, and then you hope that the telescope doesn't break and you last them a bit longer. Corot lasted for 6 years, found 32 of these transiting planets, and it was a real sort of, it was a small, cheap mission. It was a pioneer. The really interesting one was the American one, Kepler, which was launched in 2009. It died a year ago, but it didn't die completely, and it seems to be being reincarnated. What actually happened was it has gyros on it, which allow you to point. And it had 4 of them, and it could run with 3. So when one broke, it was all right. But when 2 broke, it could no longer point everywhere. So they closed it down. But actually, people have said, yes, but with 2 gyros, we can still do science. We maybe can't steer exactly where we want to go, so they're actually just about to restart it running on 2 gyros. But effectively, what I'm going to talk about finished a year ago. Now, what Kepler did, here's a picture of it. What Kepler did was to look just at a very small area of the night sky. It had about 150,000 stars in it. And say, in these 150,000 stars, how many planets can we see transiting? And this allows it then to make serious statistics, because it's looked at everything systematically in this area. It discovered something like 3,000 candidate planets. Now, if you think of it, there's a 1.5% chance by just geometry that a planet will transit when you look at it from Earth. 1.5% of 150,000 is about 2.5%. Sorry, it's about 2,500. It's seen 3,000 planets. That's because some of the stars have multiple planets, have several planets going around them. The conclusion from Kepler is that every planet, every star has planets going around it. Maybe not absolutely everyone, but virtually every star has planets going around it. So that's a complete change in 20 years from not knowing there were any planets there to now realizing that planets are common. They go around, every star has planets around it. Now, there's an awful lot come out about what these planets are like. So this is just a little map of Kepler planets. I think it's not quite up to date. Oh, it's fairly up to date. So here's what we know in the solar system for our planets. And what you can see here is that we're seeing much heavier planets because they're much easier to see. Both from the transit method and the radial velocity method, it's easier to see heavy planets. But we have seen some light ones, some ones which are the same radius of Earth. And there's a huge variety of them. They go all the way down from huge things which are 20 times as masses of Jupiter down to Earth-sized one, and there's no break. If you think of the solar system, we have 2 types of planets. We have these rocky planets, Earth, Mars, Venus, and then we have much bigger gas giants, Saturn, Jupiter, and so forth. This is continuous. And in particular, there seem to be rocky Earths which are 5 to 10 times bigger than Earth. So a whole new class of planets, we don't really know what they're like at all. We can only guess at it. So there's a lot to learn here. And what we don't know is much more than what we do know, and I'm not even going to tell you everything we do know. But you can speculate on the basis of the Kepler result. This has got a lot of publicity on the BBC website, saying there are now 17 billion Earth-like planets in the galaxy. Well, it may be 17 billion, it may be 20 billion, it may be 12 billion, but there are undoubtedly a lot. They're common. Kepler also found all sorts of other things. It found planets like Earth orbiting right next to their star, so they're incredibly hot. As Jon said in my introduction, I work on the spectroscopy of molecules. People are starting to ask me, what happens if you put rock at 2,000 Kelvin at really hot temperatures? What happens to it and things like that? So there's a whole range of science to be learned here. But I'm not going to talk about that. What I'm here to talk about is actually whether there's life on any of them and how we will find out. So here's our solar system, and we're here. What's special about here? Why do we live here? Anyone? Any ideas? What is it that makes Earth habitable compared to the other planets? Water. What sort of water? Liquid water, exactly. So the feeling is that what you need for life is liquid water. So you get this concept, which is called the habitable zone, or more poetically, the Goldilocks zone, because if you know the fairy tale, Goldilocks didn't like her porridge too hot or too cold. She liked it just right. So we don't like our water too hot or too cold. It has to be just right. And what we have here is the mass of the stars. And as stars get more massive, they get hotter. And we have the distance of the planet from the star. And the Earth is 1 atomic unit, and this is 1 solar mass. So we're here. If you get a faint star, then the planet will be quite near it if it's going to be in the habitable zone. And this is actually probably the region where the original science will be done, because it's easier to look here. We can see these sort of planets already. We're having difficulty seeing Earth-like planets around Earth-like stars at the moment. But whatever, this tells you the sort of zone where you might think there's water. Now, this is actually wrong in our solar system because there's water elsewhere, liquid water elsewhere. Anyone know where else you get liquid water in the solar system? Any ideas? Absolutely. Right. Do you know the name? No, Titan goes around Saturn. It's Europa. Actually, the satellite, so the number of places has actually been growing recently, but this is the famous one, which is Europa, which is what the lady in the audience here referred to. Europa is a big ice ball, but it has geysers on it. It has liquid oceans underneath, and it seems to have very deep lying oceans. In fact, this is reckoned to be the most likely place, if there is life on the solar system, that exists. And the heating here, why is this warm? It's not warm because of the sun. It's warm because it orbits Jupiter, and you get what's called gravitational friction. As it goes around Jupiter, the gravity pulls the middle of the planet around and heats it up. It's the same reason that Io, which is even closer to Jupiter, has volcanoes on it. And there's a satellite around Saturn, which has also recently been discovered to emit water like this as well. It's called Encephalus, but I can never pronounce it right. It's something like that. OK, so that's what sort of thing we're looking for. How are we going to find it? So I'm going to go back to a really silly experiment done 20 years ago by a gentleman called Carl Sagan. He's now dead. He was a very famous American planetary scientist. And when NASA launched a mission to Jupiter, the Galileo mission, he said to NASA, what I want you to do is to get the Galileo mission and ask the question, look at Earth with all the instruments. It had a lot of different instruments on it. Can you detect life on Earth? And there's Galileo. It was launched in 1989, took 6 years to get to Jupiter. And while it was on the way to Jupiter, he persuaded NASA to look at Earth and see whether there was any life on there. Now, they detected life in a number of different ways. Anyone got any idea what it was that they saw on Earth that gave you a signal that there was life on Earth? There's more than one right answer to this question. Any suggestions?
Street lighting.
Street lighting, so optical light. It didn't actually, funnily enough, have an optical spectrometer on it, so it didn't do that experiment, but it could have been a signature. Any other suggestions what you might see on Earth? Come on. Everyone waving? No, but everyone using one of these? No? You all have one of these or similar? Mobile phones were not quite in 1992, but television and radio were in. They saw a huge amount of radio waves and television waves, which you regard as a detection of intelligent life, okay? But they saw one other thing, which was a clear signature. They saw methane. Now, you all know that our atmosphere is made of oxygen and nitrogen, and if you release methane into an oxygen atmosphere, very quickly it oxidizes and it forms carbon dioxide and water. And they saw methane in huge quantities outside thermodynamic equilibrium, 10 to the 100 times outside thermodynamic equilibrium, and they concluded that this can only be because it has to be a continuous source on the surface of Earth replenishing the methane. And the very tasteful words of nature, these were flatulent ruminoids. Cows farting in simple English. And this is the cause of major quantities of methane in the atmosphere, and it's a clear signature in an oxygen-rich atmosphere that you've got life on the planet. And the difference between the methane signal and the radio and television signal is that I suspected these guys emitting methane, but they didn't have any television. Okay? And even if they didn't, all the vegetation here decays into what's called marsh gas, and marsh gas is just another name for methane. We know that oil wells has huge amounts of methane in it because they're decayed, fossilized debris. The signature for methane goes back millennia. So this is my attempt to capture human history on the Earth in one slide, and don't ask me any questions about it because I don't really know much about it. The Earth is about 4.5 billion years old. We started forming life pretty rapidly afterwards, after its formation, which is one of the reasons why I, like the majority of you, I suspect there's life elsewhere in the universe, simply because life is so tenacious on Earth and so easy to form on Earth. Sorry, that wasn't meant to happen just yet. And started getting oxygen probably about 1 billion years after formation. And my suspicion, I don't really know, but my suspicion is that this sort of methane signature has been observable for about 2 billion years, for something like half the lifetime of Earth. Conversely, the sort of Modern technology signatures, well, it was 100 years ago, just a little bit more, that Marconi bounced radio waves off the ionosphere, and that you can think of being the first communications revolution, which is what you'd see the signature for an intelligent life form from. So that's only 100 years against 2 billion years, and that's why I think looking for intelligent life is actually a really low probability chance. What you need to do is look for the signatures of these sort of beings rather than these sort of beings, because the chances of finding an advanced life form, unless we manage to live for billions of years, and I have to say the signs are not very good, unless we manage to live for billions of years, you're not going to see these signals. We only get one chance to look, which is now. And if you just you have to see a civilization at the right moment. So that's what we want to detect. How are we going to see it? To tell you something I suspect you all already know, but it was a shock to people when they found out, in the beginning half of the 19th century, they started measuring distances to nearby stars. And they did it using parallax, the same technique that people use to triangulate for geographical things and architecture and so forth. So they did a measurement here, and 6 months later, a measurement here. If you know what the astronomical unit is, the orbit of the Earth around the sun, and you know this angle, you can get a distance. And people were shocked at the result, because what they found was that the stars were huge distances away. They hadn't realized that. They thought somehow you could see them shining in the night sky. They were somehow nearby. And people realized that you would never travel to the stars because they were just too far away. So that this gentleman, who I suspect many of you recognize his name, came up with this very pithy statement that we were never going to know anything about the stars because they were so far away. I love this statement because it is completely and utterly wrong. We know more about the stars than we know about the middle of the Earth. And why do we know more about the composition of the stars in the middle of the Earth? Because we can take spectra of stars, the sort of spectra that some of you were taking when I handed out my spectrometers at the beginning of the talk, and we can't do that on the middle of the Earth. So if I can explain what's going on here, and actually this also dates back to the same period, a gentleman called Joseph van Fraunhofer, who was a very interesting guy, was actually an orphan. And he was apprenticed to a glassmaker who treated him unspeakably badly, but clearly taught him to make very good glass, because he made the best prisms that anyone had made. Newton before him had taken white light from the sun and used a prism and saw that you got a rainbow. But Fraunhofer's prism was better than Newton's prism. And when in a date in August 1814, so exactly 200 years ago, he took a beam of light from a shutter and used his prism and put it against a white wall, he saw not just a rainbow like Newton had seen, but in his own words, he saw thousands upon countless thousands of black lines. So this is his own drawing of what he saw. This is the flux that comes from the sun, and these are what are still called the Fraunhofer lines in the solar spectrum. If I give you a modern-day version of the same thing, this you have to think of as a very, very long strip. It's a so-called Echelle spectrosgraph, and it's just resolving the colors to very high resolution, and these black marks here are all the Fraunhofer lines. And they're lines where the sun, light from the sun, for some reason, doesn't get through. Now, Fraunhofer had not a clue what was going on. He didn't know what was blocking the sun, but he was a very good scientist, and an evening not very long later, he did the same experiment with the nearby star Betelgeuse. And if you look at Betelgeuse, it's quite red to look at, so it has a different spectrum, and he saw different lines. So he knew somehow, innately, he was looking at something that told him about the composition of the star. So the story sat there for about 50 years until an experiment which is certainly on the curriculum at schools in Britain, and I suspect most of you have done it, which was done by Bunsen and Kirchhoff, where they burnt metals in flames and looked at the colors. Have you done that? Most of you? Yes? And you get characteristic colors for different metals. And what Bunsen and Kirchhoff realized was that if you look very precisely at the colors that you emitted, they matched with some of these lines in the Fraunhofer spectrum. To take one particular example, if you burn sodium, you get a very bright yellowy-orange color, characteristic of sodium streetlights. And there's a very strong so-called D lines. The D line here, it's actually 2 lines, but Fraunhofer only thought it was 1 because he couldn't quite resolve it. Actually, the characteristic sodium lines. There's sodium in the atmosphere of the star, of the sun. So Bunsen and Kirchhoff realized that you were looking at the atomic composition of the sun by looking at these spectrum. They didn't still understand why. There was no physics theory which told them what it was that the atoms were doing, but they already realized that this was a way you could actually interpret what the stars are made of. And it took another 50 years and the revolution of which constituted quantum mechanics before people realized what was going on and that the energy levels in these atoms and indeed in molecules are what's called quantized. They have discrete values. And what you take is a bit of light which has some energy in it, and you can jump precisely between these levels, and you can go upwards by absorbing the light, which is what's happening in the solar spectrum, and you can come back down again by emitting the light, which is what's happening in your street lights or in the flame when you burn metals. So this gives you a spectral signature. People call it a fingerprint, but I much rather prefer to think of it as a barcode, the sort of thing you get in your supermarket, which you scan, has these lines on it. And every atom and every molecule has its own barcode. And if you can read that barcode, you can do it for a long way away by looking at the light. You can find out what the composition of things are, literally the other side of the galaxy or far away in the universe. So that's our secret to actually trying to find out what's going elsewhere in our galaxy and possibly outside it. So if you look at the spectrum of Earth, you look at the light coming from Earth, it changes, for instance, after photosynthesis is, of course, now. Before photosynthesis is someone's guess of what it looked like. But the point is, this is the different colors of light along here, and it looks different. And in particular, there's a signature of methane here, which wasn't there. So what we want to do that is to do that with planets going around other stars. Unfortunately, it's incredibly difficult. And just to emphasize how difficult it is, or maybe just because I like this picture so much, I'll show you this. This is a picture taken by the Voyager 1 solar system. Voyager 1 was launched in the 1970s, 1973, I think, and it's still going. It left the solar system exactly a year ago. It's the first thing, man-made thing we've had which has actually got outside the sun's orbit. It's now in the interstellar medium between the solar system. And about 10 years ago, it took this picture looking back, and this band here is the solar ecliptic, the plane in which all the planets orbit around the sun, and it's bright from the sunlight scattering off the dust in it, and this is Earth, 1 pixel from 6 billion kilometers away. This is next door. We have to look vastly further than this. It's really difficult. So how are we going to look at these planets? Well, there are a number of suggestions. One suggestion is what's called coronography, that you block out the light from the planet, from the star, to look at the planet by putting something, a coronagraph, in front of it, so that you can just resolve the light from the planet. It's what happens naturally in an eclipse of the sun. The moon happens to fit just beautifully over the sun, so you can see all the lights, all the prominences around the edge of the sun, the corona. That's why it's called a coronagraph. It's pretty difficult. If you look in visible wavelengths, the sort of light we can see, you have 1 billion times more light from the sun than you do from the planet. So this has to be incredibly efficient. It's slightly better at infrared wavelengths. If you want to look for methane and other molecules, you're better looking at longer wavelength light that we can't see. So sort of, if you have one of these lights that come up as you walk into your house automatically, they use infrared detectors looking at heat. It's about 1 photon in 1 billion. It's slightly better, but this is a very difficult experiment. But there's another way, and this is where these transiting planets come in. So it turns out that the planets that transit, we can actually look at them much more carefully. So we talked already about these radial velocity distributions where you get a sine wave as the planet goes around the star, from the star wobbling just a bit as the planet orbits it. But you get another signal if the planet actually transits. So what you can do is watch all the light from the star, and as the planet transits, this light dips, and you get what's called a transit curve, like that, going down. And the red dots here are the observational data, and the blue line is a fit through this data. And we can do this so accurately that actually there's a student at UCL who wrote a very interesting thesis on the idea that you can even see moons going around these planets, because you look very carefully at the ingress and egress curves, the coming in and the going out curves, you should be able to see a slight wobble if there happens to be a moon orbiting at the right moment. They're trying to observe one. No one has yet observed it, but he reckons that a moon the weight of Earth should be observable, and these, in general, are rather large planets, so they should have large moons. Now, unfortunately, these planets have deeply unsexy names. The naming convention is, this is a catalogue number for a star. The star is implicitly A, though no one ever gives the A. And then the nearest planet is B, C, and so forth. So this is HD 209458b. It has a year of 3.5 days. It has a mass a little bit more than half of Jupiter. That you learn from the radial velocity measurements. If you look at the transit measurements, you'll find that its radius is a little bit bigger than Jupiter. And you can put these together, and that gives you a density. And we know from that that the thing is largely made of hydrogen. But then you can take this a bit further. And here, if you want to look, one of the problems is if you want to look at the atmosphere of a planet, and the atmosphere is going to look something like Earth, you cannot do this from Earth, because you've got to look through our own atmosphere. So it's hopeless. So you have to get up into space. So NASA launched a thing called the Spitzer Space Telescope. It was all designed before anyone had even discovered an exoplanet. So it wasn't designed for looking at these planets. It was just a general purpose infrared telescope. And unfortunately, it's still there, but it's euphemistically in its hot phase, its warm phase. It was sent up with liquid helium to cool it. If you want to look for infrared, which is heat, you have to stay cool. And it had a big dewar of helium to cool it down, but all the helium has now boiled off, so it is no longer cool. So it's basically useless. But it's still there, and you still can observe with it. So Spitzer, sometime about 10 years ago, started looking at one particular planet. This is HD 189733b, and if you wonder why I remember it, I use it as my computer password most of the time. And they looked at it at different colors in the infrared. So this is the colors of light, and these are their signals. And you can see that it's blocking, the planet is moving very near its star. It's blocking something like 2.5% of the starlight. But at different wavelengths, it's blocking different amounts of the starlight. So that tells you that something in the atmosphere of the planet is blocking more starlight, say, at 6 microns than it is at 4 microns. So somehow there are different properties of the atmosphere. My colleague Giovanna Tinetti modeled this, and in this particular case, it's very hot water. There's a lot of hydrogen up there, but hydrogen is just translucent at these wavelengths. It doesn't block any of the light. But this has a very characteristic signal based on the spectrum of water. And if you wonder why I'm talking about any of this, it was actually my model for water that she used to do these observations. Now, we published this in Nature, and we submitted it with a title, Tentative Detection of Water in an Extrasolar Planet. And Nature, in their wisdom, struck the word tentative off the title and published it anyway. Luckily, we were right. So these are 3 original observations. These are later observations done with the Hubble Space Telescope. And here, they're much more accurate. You can really begin to see that there is variation in the size of the planet, effective size of the planet at different wavelengths. So what we want to do to be able to detect life is actually to do this sort of spectroscopy at great detail. And my colleague Giovanna has done this for a number of systems, detected various species, water, methane, carbon dioxide, carbon monoxide. We've yet to be able to do this on an oxygen-rich atmosphere, so the detection of methane is interesting, but it doesn't signal life as yet. And this particular planet we looked at is very hot. It's about 1200 Kelvin, hotter than the hottest setting on your oven. So it's not a good case for life. But it is definitely, this is where we want to be going. We want to be looking at the planets in this form. So what is the future? So far, there's never been any dedicated mission for finding exoplanets. Yes, I told you about 2 of them. Another one is planned by the Europeans. 2 more are planned by the European Space Agency, Cheops and Plato, and 1 is planned by the Americans, TESS. But there are no, at the moment, dedicated missions to actually work out what the planets are made of. There are ideas. This guy, Webster Cash, had this proposal for a New World observer doing coronography. So you'd have a spacecraft here, you'd have a coronagraph here, and that would block out the light from the central star here, but you would still see the planets. This is phenomenally difficult. The gap between these was meant to be 6 kilometers in space, and I don't know how much you had to line them up with, but it must be millimeters. I mean, it must be incredibly tightly aligned so that you get the thing right. This has not been selected so far, but nor is my favorite mission. We had a proposal to the European Space Agency to fly this mission called ECHO, which is Exoplanet Characterization Observatory. And basically, this was just to look at transiting planets, stare at them for a long period, and collect all the light so that you could get the spectra and you could begin to untangle what the planet was made of and potentially which ones were habitable. Now, unfortunately, this was considered too difficult at the last selection method, and they went for a rather more prosaic, let's just find more planets mission called Plato, but that's where it is. And what I hope to see, I hope in my lifetime, and I'm certain in your lifetime, we're going to see something like this flying, taking us to the point where we begin to detect life going around other planets in the universe. And that's where we are. Thank you very much.